Dilution problems are very common kinds of problems in everyday laboratory work because often we have concentrated solutions and we don't want to make up new solutions every time, so we just dilute some of these down to make more dilute solutions. Remember, the fundamental equation here that's given in your text is the fact that the molarity of a concentrated solution, m sub c, times the volume of that concentrated solution, of course, equals a certain number of moles of solute. And that would therefore, if all you've done is add solvent, equal the molarity of the now diluted solution times the volume of that diluted solution. Given again that you haven't added more solute, you just added more solvent. So the product, both those products equal each other, whatever the moles are of the solute. We can rearrange this equation algebraically and write that the molarity of the dilute solution would be the molarity of the concentrate times the volume of the concentrate, all divided by the volume of the dilute, which is just rearranging, sometimes more conveniently thought of as being the molarity of the concentrate times the volume of the concentrate divided by the volume of the dilute. In other words, that volume of concentrate by volume of dilute is sometimes called a dilution ratio. It's telling us what proportion of dilution we've done to change the molarity of the concentrated solution. Notice the molarity of the dilute is always less than the molarity of the concentrated, and therefore the ratio of volumes would have to be written such that the small volume is over the large volume, because otherwise your M sub D would come out larger than the M sub C, and you clearly can't have that. The ratio V sub C over V sub D must be less than 1. So these are very common kinds of problems where you take a certain volume of a solution, dilute it by adding a certain amount of water, and we want to know what the molarity of the new solution is. So for example, as an example, what's the molarity of a solution prepared by diluting let's say, 25.0 mils of a 6.0 molar HCl solution into a total volume, and this is important to notice, a total volume of 250 let's say 0 mils. In other words, the point here is that I've added a certain amount of water to the 25 mils of concentrate such that I end up with 250 mils of final diluted solution. This is the proper way to prepare a diluted solution. So an intuitive approach here is we know the molarity of the dilute has something to do with the fact that we were starting with 6 molar HCl. Also, we know that it's a ratio of volumes, the 250 and the 25. But how do I write a ratio times 6, making 6 come out smaller? So that tells me automatically it would have to be the 25.0 mils of concentrate I started with divided by the 250.0 mils of diluted solution, giving me 0.06 molar HCl as my diluted solution. Notice, by the way, I gave you 3 figs in one volume, 4 in the other, but only 2 in the concentration, 6.0 molar, so I can only have 2 in my answer, 0.60 molar. It's important to notice the wording on these problems, because here's a problem that's worded slightly differently. It's asking the same kind of question, but because it's worded differently, you have to notice that. This one says, what's the molarity of a solution prepared by mixing 35.0 mils of a 4.0 molar sodium chloride solution with 150.0 mils of water. In other words, roughly here, the volume of the diluted solution, I use a little squiggle over the equal to indicate that's roughly, it's 35.0 mils plus 150.0 mils, which means I have probably roughly 185.0 mils of solution. Notice these volumes, a volume of a solution plus pure water do not add up exactly the way volumes of masses do. But we can do an approximation. In fact, that's all we can do. And again, we'd say here the molarity of the diluted solution would be the 4.0 molar sodium chloride I started with times a ratio of 35 mils. Now notice divided by the 185.0 mils, not 35 divided by the 150 mils of water added. The ratio here is always a ratio of volumes of solution, nothing to do with the water added. So this will come out to 0.76 molar NaCl, again as a 2 sig fig estimate. Now, the other kind of question that often gets asked in these dilution problems is, how do I prepare a particular solution? In other words, what volume of concentrate do I need to prepare some volume of diluted solution given the molarity of the diluted that I'm trying to prepare and the molarity of the concentrate that I'm started with? Look through your algebra and you'll see that this is basically the same dilution equation I started with, but rearranged in a different way. Again, intuitively, I can look at it this way. The volume of the concentrate will never be larger than the volume of the dilute. It has to be smaller. You're adding a certain amount of some concentrated solution, pouring water on top. So when you've added water to it, your volume of dilute's bigger. So the concentrate's smaller. Therefore, and we know also that the concentration of the dilute is less than the concentration of the concentrated. You would never take a concentrated solution, add water to it, and come up with a more concentrated solution, so it's more dilute. So you have to have a ratio that is MD over MC, because that again is less than 1, and a ratio less than 1 times V sub D will give me a number V sub C smaller than V sub D. It has to work that way. So the question here is, how many milliliters of a 0.75 molar barium chloride solution do I need to prepare 100.0 mils of a 0.50 molar barium chloride solution? And again, intuitively, I know that the volume of the concentrate here would be the final volume, that's 100 mils that I'm trying to prepare this diluted solution, and the ratio has to be written 0.50 molar over 0.75 molar, which works out to be 67 mils as a 2 sig fig estimate based on the 2 molarities I gave you. Now, the volume of water roughly needed to make this, of course, if somebody asks you that question, the rough volume of water is going to be the 100 mils of diluted solution you're trying to prepare minus the 67 mils of the concentrated solution you're using, and that comes out to 33 mils. But again, it's very important to distinguish between volumes of water added and final volumes of solutions.